Hello? Hello, can you hear me? Am I holding the mic in the right spot? Excellent. And now for the best part, the power supply stuff, power systems, my favorite anyway. I'm Shaun Harris, I'm with Microsoft. I manage the power team and the cloud server group, and Hamid and I are going to tag team on this presentation and walk through the concept of the V3.
Okay. Hello, everyone. My name is Hamid. I'm supporting the power system at Facebook. And today we are going to co-present our progress that we have done on the OpenRAC V3 power system. So the OpenRAC V3, there are several new features that we are going to add on a V3 system. Basically, we are going to move to one power zone with a flexible location anywhere in the rack, and it is based off 48-volt system. This is a good time that we are going to transition to 48 volt as the rack power is going to increase more and more. It's a good time we switch to this solution, and we know that it's going to pay off over time. The power and battery system, they are flexible and modular. You can have as much as power you can place in the rack, and we will go through it. And the battery is also optional. You can have more or less. If you want more backup time, you can add more. It's just like you have all the flexibility with this solution as much as you want to do. Comparing with the V2, that the battery was dependent of the rectifier power system, the battery is completely dependent module. So it completely runs dependently, and you will have the maximum reliability out of it. We are going to leverage the Microsoft 7-pin concept, and we are using it in this our approach. That 7-pin will give us the flexibility to have the different voltage configurations. And the battery, as we go later, you will see that it will have it can provide, because it's regulated, it will provide peak power shaving on transients. So there are 7 components we are going to introduce, and we are going to develop through this OpenRAC V3, and we are going to go through it today with Shaun. There are three versions of the power shelves that we will go through, which support from 15 kilowatt, like 17.2 and 18 up, and it can go up as much as you want. We are introducing 3 kilowatt rectifier with a 48 volt. There is a shelf management controller that we are going to use for both power shelf and battery shelf. The output connector is pluggable. We'll talk about that. The 7-pin connector I just said, there is a 7-pin universal input, and then there's a battery shelf and battery module. So these are the 7 components. I think you're going to start?
Oh, you go ahead.
Okay. So the rectifier, so the starting point that we start to talk to be common ground on the rectifier, we decided to go with the rectifier that we landed to go with this solution. It's single phase 200 to 277 with plus minus 10%, which would be 180 to 305. So support a large range of voltage. Works with both 50 and 60 volt. It is a fixed output voltage, just 50 volt fixed. It's not going to be like OpenRAC V3 with a wide voltage range. There's a narrow range concept that I'm going to go through it at the end of this presentation. We are going to set up the limit for the efficiency and a lot of other things, but the main things like the efficiency and some other THT and other things, we are setting at a minimum of efficiency of 97.5 at the peak and 96.5 at full load. Of course, you guys can go above that. I wouldn't complain. The current sharing and the communication, we had a lot of good discussion there, and with a lot of you guys' support. We decided to go with the analog current sharing that we know it is simpler to implement and it's more reliable. There is a droop on the rectifiers that it will give 5 to 10% of current sharing, but this is with active current sharing through analog current bus. We can get up to 2-3% accuracy. And by the way, this per spec, You can enable or disable it, or you can decrease or increase the amount of droop that you want. So that's all the detail is there on the spec. And the communication between the rectifier to the self SMC is through PM bus. It's a simple solution that I think it's well established in the industry through the PM bus, and the goal is that the rectifier should work with each other, even if the SMC is broken, it's not there, or any other way.
Okay, so the power supply, that 3 kilowatt power supply, is the common point for all these platforms. It works well for the Facebook case. It works well for the Microsoft portfolios. So we're targeting 3 kilowatts, and 97.5% is, I would say, the minimum expected. We want efficiencies as high as possible. Entertain 99% if you can get there. So 3 basic options based upon that 3 kilowatt rectifier. Option 1 is a N+1 available system. 6 power supplies, 3 kilowatts, 15 kilowatt type of applications. 1U, it is using the new developed 7-wire connection. Again, wide range input, 200 to 277. No breakers in the box, direct connection to the overhead whip, no PDUs in the system. We're simplifying that. This is a representation of what the system will probably look like. You can see on the left side, you see 6 power supplies and an SMC controller. On the back side, you have the 48 volt connector as well as the universal power connection. If we go on to the second option, it's a 2-corded system, but it's still considered N+1. We're going down in cord ampacity to get to this type of power per rack. Same application results, 15 kilowatts N+1, no PDU, no breakers in the rack, direct connection to the overhead or underfloor. Option 3 is more towards the Microsoft solution space. This is an N+N, highly available platform 2U. Where in this case, you've got 6 times 3, so you got 18 kilowatts at N+N. If you want to do an N+1 in this configuration, you can get it up to 33 in this 2U shelf. So you can see how the 3 kilowatt form factor really fits across the suite. A 4,000 kilowatt doesn't really help us a whole lot, but the next step would be a 6,000 kilowatt in this space. But we're going to focus on 3 kilowatts today. This is a representation of what the 2U system would look like. This is in the early concept stage, so it may change a little bit. But you can see we've got 12 power supplies, an SMC controller on the right-hand side, and that's the same controller as you would see in the 1U space also. In our space, we're using the larger 7-wire connections that we have in production today. As the smaller connector develops, we may transition to that. It depends on a couple of things that need to come together. But you can see we're using the same 3 kilowatt power supplies. With respect to the SMC controller, that is the element that marries the power system to the facility communication or control fabric for this particular rack. More than one way to do that. We're allowing for an RS-485, we're allowing for Ethernet, depending on what you need. We're hoping to make this very flexible, and as Hamid said, PM bus, but from that SMC to the power supplies, you'll be able to read telemetry, PSU health, power consumption, all those sorts of things, as well as you upgrade, downgrade firmware, and do all battery test commands. It's the same SMC controller for the battery shelf also. Moving on, this is representation of the new 7-wire connection that we're looking at. It is a lower profile, will fit into a 1U case. Same electrical connect as we see in the Olympus product line. Any questions on this front? Sometimes this causes some confusion. A little bit on the 48 volt connection. We're using the existing connector. It's 500 amps per connection. It is a floating connection. We're not bolting to the bus bar anymore. That addresses some shake and vibration stresses between a 48U bus bar and a power shelf. They will float independently of each other. In a 18 or 15 kilowatt application, you'll use one connector. In the 2U applications, you'll use 2 connectors, but it's the same connector. This is the battery module set. And do you want to talk a little bit about this?
Yeah. So this is the second, because this is the last piece of this power system, the battery module. The battery module is like completely separate module. Yeah, with the same output connector. You can put it anywhere in the rack, or if you don't want to use it, you don't use it. Or the other way is that you want for some application more backup time, like 10 minutes backup time or 15 minutes backup time. You can add another shelf, and so you can adjust it. We got the feedback from the workshop from you guys. You all, we are going to target it with a 2U solution. With that 2U, we are thinking it's going to be 600 watt-hour, and we are going to think about, we are designing our base initial design. We think we can get like up to 3 to 5 minutes backup time with and match the power shelf, like 15 kilowatt. The way that we are actually thinking about, and as I said, this is a regulated approach, and the way that we are thinking about it, it would be the battery packs, and at the end there is like another box. That's a DC-DC converter. So this is completely modular. So that DC-DC box attached to the battery module, and then you slide it to the rack. The reason that we did this is that the DC-DC converter, we can go to the power companies and just leverage their expertise. For the battery pack, we go to the battery expert and get the input. And the power shelf, the shelf, it could come from different suppliers. There are benefit to do the regulated approach compared to V2 that was basically unregulated battery. The benefit is that the batteries with the DC to DC converter after the pack, the batteries will share current equally, and they age similarly. So not like one unit has a slightly higher voltage. It will just start to share, but the other don't. And you can allow the mixing of old and new batteries on the same shelf. With an unregulated approach, you always need to match them. So they should always be similar age, similar charge level. It's at higher scale, data center scale, it could cause problems. But this one, you don't need to care. If one battery is dead, you take it out, you put another one. It's okay that they are old and new. And it will allow the peak power shaving. I will talk about that. And the voltage that we are thinking about this is like fixed 48 volt. The Rectifier 50, the battery is 48 volt. I will go over it later on. Next slide. So these are some of the configs that you can think about. So the first one is like you put 1U with 1U option 1 or 2 with 6 rectifier. You can easily get to 15 kilowatt with M+1 approach. The power cord comes in. This one, like example, doesn't have a battery. So you just 15 kilowatt without backup. You might have your backup somewhere else. So you don't need to have a battery on the rack. The second one from the left, it's a battery. It's the same thing with the battery, 2U batteries, and you have a 15 kilowatt with backup. And it can be anywhere. You can have, like, one good example is you have your power stuff on the top and battery on the bottom. And you can benefit having this because usually at the bottom is temperature is lower compared to some other locations. You can have them, if you like, at the middle, both of them at the middle as option number 3. The power entry can come from the top or can come from the bottom. There is no limitation on that. The option, the other option is like, this is like option 3. One example, option 3. With M+N, you can get 18 kilowatt, and it's like without backup. Again, you can add a backup. You can add whatever fits you the best.
And this slide shows some concepts from the Microsoft side. The left-hand side is a view from the top of the rack and how it orients itself. 200 millimeters cable routing in the front. We've got the existing Harding connector in the back with cable routing. We started off with a single power shelf at 17.2 kilowatts because that's dictated by our power cord. Once we started socializing it and we started looking at the freedom that the connector, 48 volt connector on the back of the tray gave us, we had one guy come back and say, I really want 4 of these power shelves in a rack. And that gets us to 68 kilowatts, which really drives us into needing the liquid cooling manifold. So this is becoming a very modular concept. We can meet a 15 kilowatt or 68 kilowatt solution. So it's a little bit exciting right now because I don't know where this is going to end. Okay. There you go.
Okay. So the new concept that we are proposing actually as part of this V3 is the concept of narrow range 48 volt. An open rack V2 that I was an author with the other folks a few years ago. There was a lot of feedback from the community that this voltage range is too wide, 40 to 60, designing a rectifier with nominal of 54 that works down to 48 volt is difficult. The bus bar has to be designed with a nominal of 54, but that also needs to work with 40 volt, which means that 54 divided by 40 is like 36% more. So it's like bus bar should be thicker by 36%, the connectors, everything, but we rarely go there. There's a corner case you have to support. So it adds to the cost, but we rarely use that. And the other problem was at the server side, since the voltage is 40 to 60, you cannot use 60 volt component. You need to go to next step, next component voltage, which is 100 volt. So like all the hot swap controller, capacitor, switch, MOSFET, they need to be like, normally the next component level is 100. You have to go to 100. So it has both complexity of the voltage and the current. And then there was also the battery complexity that also I discussed before, like old and new batteries, charge and discharge batteries. What we're trying to propose at this solution, and basically that 40 to 60 voltage concept on V2 was designed for lead acid solution that they actually float the battery on the bus. Since we are going to use like lithium-ion batteries in the data center widely, the best option is like just optimize it for that lithium-ion and technology available today. So we are actually, as part of this one, we are adding one component. That is the only one component we are going to add. The rest is the same as before. Like you have a rectifier with ideal diode, it was as before, and then we are just going to add another DC. We are just introducing this component that actually regulate the bus, just regulate the battery, which probably would be in the range of 40 to 60 down to 48 volt. So what you would have normally is like at the rectifier you would have 50 volt, at the battery you have 48 volt, and there are 2 diodes connected. So normally the rectifier runs, the voltage is 50 volt. When there is a outage, rectifier problem, any other things, the voltage goes to 48 volt, and then it goes back to 50 volt. And then the voltage comes back, it goes back to 50 volt. It's just the range of the voltage. As a very simple that I'm going to present today, it's just 2 volt. We need to consider the droop, voltage drops, and other things that I had done the details, and it was on one of the monthly guides I went to do it's very detailed. It will add another more details to that, but it's basically working, and there is no problem with that. So that's just basically the concept that we are going to introduce. Again, if you don't have a battery, no problem. Your voltage is like 50 volt fix, and you just deliver it to server. And the server needs to just deal with 50. Otherwise, it just will be 50 or 48 volt. The benefit of this approach is basically it reduces the component size. You just need, since the voltage range is low, your current range would be low, and you just can use nominal, the current close to the nominal doesn't vary too much, and you can just use the 60 volt components. And then the technology available today that I was trying to talk, it is the this concept of 4:1 fixed ratio converter that has been in industry, introduced in industry over a couple of years ago, this concept of using switch capacitors or fixed PWM, they are efficient solution. And by this approach, we are optimizing for using this technology. With the conventional 40 to 60 volt open rack V2, the output voltage with the 4-to-1 converter would be 10 to 15. 15 volt is very high. Most of the conventional point of load converter doesn't work 15. With this one, we have done the analysis and we know it's 12 volt plus minus 10% we can easily achieve. No problem. I think we can do better than that. The detail was on that conference call that it was in the monthly call. We think we can get to 7%. I don't think we can get to 5%. We need to add to the cost if we go to 5%, but 10% is easily to achieve. Most of the conventional point of load converters, they run easily with 10%. And if you want better than that, just use the regulated version. And still you benefit because you use 60 volt component. The good thing about here is that the power will flow naturally. You don't need to have a software, hey, battery turn on, battery turn off. That battery didn't turn on, so you don't need to have a lot of software on the V2 that command the battery turn off to off. It just flows naturally, and it's very simple design. So that was all we already work. I'm very excited that we work with Facebook and Microsoft, and we landed to a solution that actually fits our need. I just want to say that toward this work, we did both Microsoft and Facebook, we did compromise. So some here and there we had to change. We had to let's give up those 2 millimeter and give up that voltage. So we come up with that solution. I'm going to suggest and propose to all other end users that if you guys are interested in this solution, and if you think that in now or maybe sometime in future, this solution works with you, come and join us, and we can actually work out with you. If this is within the range, if it is a completely different solution that you have with a different depth and other things, probably not. But if it is very close to that solution, come and work with us. Our goal through OCP is that we try to converge on both the rack and the power. We try to converge to one similar approach. It is a win-win for both end consumers and the suppliers. It is both for us. We are already on OCP. We have too many racks introduced. We are part of V3. We are trying to converge. So I'm encouraging everyone that spread this word. If you guys interested with this solution, and if you have some more requirement you want to add, and you may think you are going to use it in now and future, please reach out. We will post the first round of a spec probably somewhere in October in a wiki. Please provide feedback. If you are more interested, please join us. And last but not least, please, I think you can join our mailing list, Open Rack and Power. I think if you send an empty email to this one, you will join on the mailing list, and you can get involved. Thank you.